Welcome back. It's a pleasure to start this morning with a talk on the observational axis of the workshop. This will be David Nichols telling us about detection prospects of memory effects from binary black holes. And please do not hesitate in asking questions, interrupting him, and making it into a discussion as much as possible for the next hour. I'll let you know when you are running out of time so that you can.
All right, well, yeah, thank you very much for that introduction, Simone, and thank you to all the organizers for putting together this, exciting and diverse set of topics. I know from organizing one of these things, it's not a non-trivial task, right? So for today, as Simone introduced, I'm going to tell you a little bit about the observational side of this. So namely, what we can learn about, say, the structure of asymptotic infinity from these gravitational waves, specifically this offset here known as the memory. Because as you may or may not be aware, essentially we can extrapolate from our observations that every 15 minutes, two binary black holes like these are merging somewhere in our universe. And this gives us, I think, a remarkable opportunity to actually probe some of the subtle aspects of the infrared aspects of gravity that have been discussed primarily theoretically so far in this talk, or in this conference rather. So what I plan to do is probably too ambitious for an hour, but I have 5 topics. The general, I guess, logic behind it is I'll say a few very brief words about trying to measure gravitational wave memory with pulsar timing arrays. The reason why I think this is interesting is it's actually sort of the most obvious measurement of the memory. Like you really are measuring, say, this final offset. That's what they're searching for. The downside of it is that it's hard. You're going to have to wait decades probably. So the bulk of my talk then will be about what we can do with the data currently, these gravitational wave mergers from binary black holes that are happening every 15 minutes in our universe. So I'll talk about, just what the detections are, how you actually measure, and what it is that you measure related to the memory with interferometers, and what the prospects are. And then this is, the question mark whether I'll be able to make it past detection of memory, but if I do, I'll talk about some higher order memory effects, things like spin memory, and in principle, an infinite sequence of memory effects that one, again, in principle can measure. In practice, I think it's going to be very challenging. So just to make sure everyone's sort of on the same page, as in electromagnetic astronomy, there's a frequency bandwidth of gravitational wave sources that one can measure. And they range from probably the most familiar, the ground-based experiments, which have been detecting gravitational waves since 2015, to longer periods or lower frequencies like the LISA mission, which is actually slated to be launched in 2035. It's adopted as an ESA mission. So this will happen as far as we can tell. And as we keep moving to lower frequencies or longer periods, there's pulsar timing arrays, which back 2 summers ago in 2023 announced something that's on the cusp of the confident detection of the gravitational wave background from essentially all the mergers of supermassive black holes that are going on in the galaxy or in the universe throughout the duration of pulsar timing arrays measurements. I won't get to say anything about the ongoing search for cosmic microwave. Is the sound okay or?
No.
Okay.
It's just a point of form. There are 2 conditioners that are off.
Okay, sure. Yeah, understood. Okay, so as I was saying, I won't discuss the search for essentially the B modes, the sign of primordial gravitational waves in the early universe. That'll be, that's not asymptotically flat, so that's my excuse. Okay, so let me jump into essentially the first part, which is this 4 sigma detect, or sorry, I won't say so much about the detection itself. I'll discuss more the prospects of detecting gravitational wave memory with pulsar timing arrays. And the next part will essentially be, the majority of the talk will be about the ground-based experiments. So let me just remind you briefly about what a pulsar timing array is. This is a nice schematic cartoon of it, where essentially these dots surrounding the Earth here are pulsars, which emit radio bursts. Basically, they're irregularly shaped pulses of radio waves, but they arrive with an extreme irregularity. So namely, every 10 milliseconds, one of these pulses come, and pulsar timing experts are so good at predicting when the pulses come, they measure maybe once every couple weeks or every month or so. And they do this for decades. and they can measure essentially when this pulse will arrive at Earth with the precision of order 100 nanoseconds, over decades. And if you have, say, a gravitational wave, as illustrated, with this schematic embedding diagram here, this will cause a very small change in the arrival time of these pulses. Okay, so then what is kind of the principal observable that pulsar timing people try to measure? They measure this timing delay, tau, as a function of time t. And a short exercise one can show, you can look in Maggiori's book on gravitational waves. Essentially, the timing delay is related to the difference of the strain at the Earth versus the strain, when it was emitted, the retarded time at which it was emitted at the pulsar. So I'll use this as a nice demonstration. Let's go from optical to mechanical. Suppose I have, a burst of gravitational waves. So I have memory here, I have a non-zero h here, and I have a zero h over here. Okay, so this observable says that these pulsars here will not have any timing delay because h is 0. As the wave passes by, right now there's a non-zero h, and as time progresses, h will be growing, the tau will be growing linearly with time because h is just a constant. And in fact, since it's coming from here, you won't see any delay from these pulsars because the burst memory has already appeared. So there's a very obvious observable. You just look for a timing residual that grows linearly with time. And this is what pulsar timing does. They assume a very simple sort of step model function of what the memory looks like. And they look for this linearly growing time delay. So they've done this, right? This is an actual constraint, yeah? Kiloparsecs. So they're in the galaxy, so 10,000 light years.
Okay. And the other is, so these are all on inertial trajectories, these pulsars, right?
Some of them are in binaries, so they have to model out the motion of the binary, for example.
Okay, but the center of mass of the binary is, you wouldn't be comparing the time delay of two pulsars in a binary, right? Would you?
I don't think there are any binary pulsars where they're timing both pulsars. I think most of the pulsars in the binaries are, with a white dwarf or some other companion that they don't measure in radio.
Yeah. So nearby inertial detectors, when a gravitational wave passes, don't get a relative time delay. They get a relative displacement. What is different about this here?
So you're measuring essentially a difference in the strain at the pulsar versus at the Earth, separated by 10,000 light years, essentially. So as opposed to LIGO, where you're looking at distances, relative displacements, essentially kilometers away, here you're looking 10,000. And you instead measure a timing delay rather than displacement, because that's the observable they prefer to measure, essentially. They can predict how frequently these pulses are going to come.
Okay, so that must be a second order in the separation.
No, essentially the observable that they measure is if you have some period of your pulsar t, then you measure a delta t over t, and it's essentially this, integrated dt. That's what this timing delay. And if you work out what the delta t is, what the perceived time, I guess, at Earth, how much longer or how advanced or delayed it is compared to just a flat trajectory or travel through the galaxy without the gravitational wave, let's say, this is what you measure. Some weird feedback. Is that clearer?
Not completely, but let's talk about it later.
Okay, sure.
But maybe one could say that LIGO also measures time delay. It's just that under the approximation that the wavelength is much bigger than the size of the detector. You can also interpret that as a space displacement, maybe?
Yeah, you can also think, in some sense, you can think of doing a kind of standard displacement measurement just between the Earth and the pulsar. It's just that in practice you don't really know the distance to the pulsar that well, so it's a relative change, and that's why you think in terms of these timing delays, because when the pulses are going to arrive at Earth, you don't really know the distance that well. Okay.
More questions?
Yeah.
A very naive doubt from a complete outsider's perspective. I mean, this works if, conceptually very well if you have some like nothing, and then one wave train passes, and then your explanation with the stick works perfectly. But then if you have a statistic thing, it sounds a lot more difficult, right? Because if these things continuously arrive from all directions, I mean, there's this background, right? So
yeah, so I haven't discussed the actual measurement of the stochastic background, but there it's more complicated, right? Pulsars, I've brushed this under the rug, but they're actually kind of noisy. So they have just some intrinsic red noise. So they essentially, do a fitting where they look for something that looks like noise associated with just, random glitches in the pulsars, and then a correlated noise between all the different pulsars due to the superposition of gravitational waves from supermassive binaries moving in all directions. So the spectrum of the noise, the power law, if you like to think as a function of frequency, differs for the glitches that pulsars have than from a stochastic background. And the most important observable is there's a correlation, right? If you have a pulsar glitching, the one on this part of the sky versus the other part of the sky, they're going to be uncorrelated. Whereas essentially there's an angular correlation function called the Hellings-Downs curve, which is how you actually determine that the noise that you're seeing from all the superpositions of mergers is coming from a gravitational wave background and not just from other astrophysical sources. Okay, so let me then discuss what this plot here is showing. So this is an upper limit on the strain, not assuming any particular source, just assuming this very simple step function model of a burst with gravitational wave burst with memory. And all these stars are the locations of the pulsars on the sky in equatorial coordinates, so right ascension and declination. And as you can see, they put constraints on how large the gravitational wave strain can be, and where you have more pulsars, you get a better constraint, and the idea is it's somewhere between 10 to the minus 14 and 10 to the minus 13. This is kind of the characteristic range. And just as a comment, they actually have to subtract off this correlated background from the superposition of many supermassive binary black hole mergers to be able to do this search. All right, so this seems great, right? This is basically what you want to measure. The problem is the astrophysics side. So this is a kind of complicated plot here, but basically it's comparing two different data sets. So 15 years of pulsar timing ray data, or 12 and a half. And then it's comparing two kinds of searches. One where they only look for essentially bursts with memory that pass by the Earth, that's Earth term. And then PSR is pulsar term, where they also look for just gravitational wave bursts with memory that pass by a single pulsar in the array. Okay, so what you can see how to interpret this is basically, this is an event rate upper limit in number of events per year. And since they didn't find anything, this number that it goes to is roughly 1 over 12 and a half or 1 over 15, right? You can't really constrain it any better than the length of your data set. And then this axis right here is kind of, the best upper limit they have on the sky, which is of order 10 to the minus 14. It turns out that, there's kind of, look elsewhere effects. So actually including the pulsar terms gets you a slightly worse sensitivity, but because these pulsars are located at different distances, you get a huge benefit in terms of the event rate, right? So if you sum up 100 pulsars times 15 years, you get on the order of whatever that is, 1,500 years of data. So that's why you can put much stronger constraints. All right, so then now the depressing part, this is, if you ask astrophysicists, what do you think is the rate of binary black hole mergers that happen, and produce throughout the universe and produce a burst with memory with a strain of order 10 to the minus 14? It happens once every billion years. Okay, so pulsar timing, I think, is the measurement that you want to make if you want to detect a burst with memory. The problem is that essentially you just have to keep adding pulsars to keep pushing this down and timing it longer and longer to get more precision until maybe in several decades you're starting to approach where astrophysicists actually think you'll be able to measure a supermassive black hole merger. All right, so this is kind of the state of pulsar timing. It's the measurement that you want to make, but unfortunately we'll just have to wait a very long time. So this is all I was planning to say about pulsar timing. So if you have any questions, this would be a good time to ask. All right, if not, then I'll move on to essentially the data that we have, which is from the LIGO, Virgo, and hopefully very soon Kagra detector. Okay, so LIGO and Virgo you're probably most familiar with. Kagra is a detector in Japan. It's underground. That's why it's shown in this more schematic diagram. It's in the Kamioka mine. Super Kamiokande is co-located there. And what LIGO measures is essentially strain, and it does most of its analyses in the frequency domain. So people in the LIGO world like to plot these gravitational wave amplitude spectral density curves. And what they mean is that, if you look in the frequency domain, it's a Gaussian process, it's zero mean, and the characteristic standard deviation at that frequency, is given by a point along this curve. So all these funny, spikes here, some of these are related to like just, the power lines in the US at 60 Hertz or at 50 in Europe. And then these are optomechanical systems. They have a bunch of resonances. They have all these spikes here. But the sort of key point is that LIGO has a finite frequency bandwidth. It only measures frequencies above 10 Hertz and then up to, a few thousand Hertz. Okay, but still, right, this is a remarkable experimental achievement. If you look at these 4-kilometer detectors, right, the absolute strains that you're measuring are like 10 to the minus 19 meters. And just as, a brief comment, this is, what it looked like on April Fool's Day, so not a joke. It turns out that LIGO took a commissioning break on that day, and it was supposed to start up again today to begin observing. Okay, so just as a comment, I think Paolo mentioned this, but this is, what a gravitational wave signal looks like. There's a long in spiral in which the frequency slowly increases, the amplitude of the signal increases until the merger process, where at some retarded time, the black holes are actually coming together. And then there's the ring down where it settles down to a single black hole. And you might ask, why do I care about all these details? Well, for essentially all the binary black hole mergers that have been found, they're below the threshold of the noise. So you need to do a data analysis process called match filter, cross-correlate the signal with the LIGO data to pick out the ideal template. And without it, you can do some excess power searches and so on, but you can't really learn much about the signal. So you need to know what the signal looks like to get useful information about it. Okay, so what has LIGO detected? So in the information about how the frequency and amplitude grows and how the final black hole rings down, there's information about the masses, and astronomers prefer to measure these in solar masses. So for the example, the first event had a 30 and 35 solar mass black hole, which formed a 62 solar mass black hole. And during the first 2 years of operation of LIGO, 1 year of actual observing time, there was a commissioning break again. 9 events were detected, including a merger of 2 neutron stars. The detectors then essentially underwent another upgrade for about 2 years and a half. And they split the observing run into 2 6-month blocks. And this is what the population of binary black holes, binary neutron stars, and black hole neutron star binaries look like after roughly another year of observing, right? It grew roughly 8-fold because the sensitivity of the detectors grew by a factor of 2. So the volume of space that you explore is basically a factor of 8 larger. So it's all kind of what you'd expect. All right, so then this is a familiar date because this is when the pandemic started. So LIGO also happened to shut down then and underwent significant or non-trivial, let's say, improvements and started its 4th observing run in, say, early 2023. And its 4th observing run is split into 3 blocks, O4A, B, and C. And what I'm showing here is just something from a website called GraceDB, where whenever there's a gravitational wave event, so this one, for example, was on the 31st of March, 2025, they put out this announcement so that optical astronomers or radio astronomers can follow up the event if they'd like. So these are candidates. They're not significant detections, but they give a false alarm rate here, which tells you, roughly how significant this is. So this event was, had a false alarm rate of 1 in a century, which is, pretty good. Okay, so essentially after 6 more months of observing, 81 candidates were detected, but offline searches tend to be more sensitive. So probably when this result comes out soon, it'll be, more than 80 events that are actually confirmed. Then another 8-month block found, another 100 more events. And then there's this sort of 2-month run, which got interrupted for this commissioning break, where another, 20 or so events were found. So during the past 2 years, LIGO's been working hard and detecting hundreds of gravitational wave events. All right, so the question is, why are these sort of interesting from the perspective of asymptotically flat spacetimes? So I'll give my, astrophysical viewpoint on this by discussing something which is known as the Planck luminosity, c⁵/g. So why the Planck luminosity? Well, it is indeed a Planck mass e², radiated in a Planck time, but obviously h bar cancels in this, so it's something that classical systems can achieve. So if you think about the most relativistic binary in the solar system, that would be Mercury and the sun. If you do a naive quadrupole calculation, it turns out it's radiating about 1 watt of power, so less than the average light bulb in gravitational waves. So whereas something like a galactic source binary pulsars, just coincidentally, these have a luminosity in gravitational waves that's comparable to the optical luminosity of the sun. And it's essentially for this reason that the first evidence for gravitational waves in the Hulse-Taylor binary through the evolution of the orbital elements of the binary was able to be confirmed and shown that it's in complete agreement with the quadrupole formula that Einstein predicted back in 1918, I guess, correctly, and Eddington then corrected in 2022. No, sorry, 1922, not 3 years ago. All right, so binary black holes, I'd say, are interesting. Yeah. No, Einstein computed in 1918, but he had a factor of 2 error, and then Eddington computed in 1922 and corrected this factor of 2 error.
But then in the 30s, he wrote a paper saying gravitational waves don't exist, right?
Yeah, so he did it in the linearized approximation, and then he did this work with Rosen, I believe it's Rosen, in the 30s, where he was looking at nonlinear solutions, so cylindrical waves, and convinced himself that they don't exist. But then, yeah, there's this famous story about how this paper was refereed. I'm forgetting who the referee was at the moment. And Einstein, of course, was not happy that his paper was sent to be refereed. He sent it to Phys Rev to be published, not refereed, of course. So, yeah, so apparently he never attempted to publish in Phys Rev after this. There's an amusing story. There's this book by Daniel Kennefic, which called Traveling at the Speed of Thought, which is from this Eddington paper, which describes all this very nicely. Okay, that was a bit of a digression. To get back to the main point here, I wanted to essentially say why are gravitational waves interesting as a source, from the perspective of asymptotically flat spacetimes. And the idea is that they have a peak luminosity, so around the merger time, of 10 to the minus 3 in these Planck units. So namely, they radiate about 1% of the rest mass energy of the black holes. So this is M1 plus M2 in a dynamical time that's like 10 M. Okay, so these are extremely luminous systems. And what that means is we really do need to think about things in terms of the Bondi-Sachs or some kind of nonlinear framework, because the news that you get is non-trivial. These nonlinear effects are significant even in the wave zone, even the interaction between the waves themselves. All right, so let me then just give the lightning review of the Bondi-Sachs framework, mostly just to introduce my notation for things so I can say a little more concretely what it means to measure the memory effect. So I think this is basically identical to the notation that Massimo was using in his talk, so I won't say very much about it. But for me, basically, theta A are my angular coordinates, U and R are the usual Bondi coordinates, and this is the form of the metric. So if you essentially expand the metric in 1 over R, no polyhomogeneous things, then the most important variables in the story are the shear tensor, the news, its partial derivative with respect to U, Then the bonding mass aspect, you know, and the U component of the metric, the angular momentum aspect, the subleading part of the U theta part of the metric. And then time permitting, I'll say a few words about this EAB tensor. So this is kind of like a subleading part of the, you know, trace-free part of the two-sphere metric, which you can think of as a kind of quadrupole like aspect. So, you know, mass, angular momentum, quadrupole, essentially. All right, so then let me just give a brief review of the dynamical equations, because these are what I'll use to actually compute memory effects. All right, so I'm doing something which looks a bit crazy. I have C's and G's in here, but I'm illustrating a point here, right? Essentially what the evolution equation for the mass aspect is, if you were to store C's and G's, you measure essentially the shear in units of length and news as a velocity, right? Then you see the Planck luminosity popping out here. So in other words, right, what this is saying is the power per solid angle, you know, luminosity, is set naturally by c to the 5 over g. And then since the news has units of velocity in here, right, during binary black hole mergers, the peak luminosity is of order 10 to the minus 3. So the news is of order, you know, 10 to the minus 1.5, basically. So, you know, this gives you a sense of why you might actually need nonlinear effects. This is not that small a parameter, at least by my standards. Okay, and, you know, then there's a similar kind of equation for the angular momentum aspect. The main difference that you might notice is that instead of the electric part of the shear, or news in this case, appearing in the evolution equation, this combination here only gives you information about the magnetic part of the shear. And interestingly, it's also sort of suppressed by a factor of c, right? This has an explicit length scale from the shear coming in here and from, you know, whatever the size of your object is that you're computing the angular momentum of. So as you go, you know, higher order in 1 over r, you also, you know, have a decrease in c. So if you then go to the next order, this evolution equation for the quadrupole-like moment, the E, then again, you sort of continue to see this suppression. It's one factor of c weaker, and you start even seeing, you know, cubic terms and things, you know, get quite a bit uglier. Yes.
In your expansion, you assume peeling, right?
You
assume the peeling property.
That's right, yeah. Yeah, so no log R terms or anything like this.
Would anything significant change if there is the first term is log R over R cube instead of being 1 over R cube?
Yeah, probably Mark is the person to ask about this, because he's done a nice calculation of, you know, what happens if you don't assume peeling. The structure of the equations is interesting. You know, the terms involving logs in some sense start decoupling from the main Bondi equations in a way that I probably can't describe too accurately at the moment. But I don't think it would change in any significant way any of these evolution equations, basically.
Sorry, there's a power of, is there a power of R, and what are the units there? NAB can be of order 10 to the minus 1.5 C.
Yeah, so I'm measuring shear. Let me just go back to the metric. You know, so I'm doing something that's maybe a little weird. I'm measuring C in units of length and then E in units of quadrupole, so mass times length squared. So yeah, this is the only place where I included C and G just for illustrative purposes. So then, you know, news is partial U, so you just, if you take d by dt, then it has units of velocity. So I'm just doing this here to kind of show where this Planck luminosity comes in explicitly, but, you know, subsequently I'll drop all the G's and C's just for clarity. Okay, yeah, so let me just say, you know, what the memory effect is. I think I mentioned this in words, right? This C you can decompose in this Helmholtz like decomposition into, say, a electric parity and a magnetic parity part. And if you look at, say, essentially the conservation equation for the angular momentum aspect, if you integrate from some reference time u1 to some later time u, right, you'll generically get a change in the electric part of C that's going to be constrained by the change in this, you know, charge, the mass aspect. And then this flux term, I added in stress energy just for fun. So of any matter fields, and then essentially the stress energy of gravitational waves. Okay, so LIGO in some sense is basically just measuring this shear tensor in a special polarization basis, the plus and cross basis. So they measure H plus minus IH cross, and they expand in spherical harmonics and so on. So what it's saying is, with LIGO, you generically expect to measure some change in the plus polarization related to this change in the electric part of the shear. All right, but there's, a subtlety about this. So, right, as I mentioned earlier, LIGO has a low frequency cutoff. It doesn't measure frequencies below 10 hertz. So LIGO doesn't really directly measure this delta CAB in the same way that pulsar timing, does try to measure the lasting offset, and that's the signal it looks for. But what you can do with LIGO, right, if you have a zero mean signal and then it goes to non-zero, right, something must be ramping up. There must be some component of the signal that goes from 0 to non-zero. So this is what I'm calling the memory signal. And it turns out, you can essentially compute it from this kind of conservation law requiring a consistency of it. And although you can't measure, the delta function at 0 frequency associated with this final offset, there also is a 1 over f behavior, right? If you Fourier transform a step function, it's a delta function plus a pole and 1 over f. And you can measure this part of the pole in the frequency range that LIGO can measure. Okay, so this is what I mean by trying to measure the memory effect with LIGO. And what's interesting is for binary black hole mergers, essentially this term right here, the nonlinear flux term, is the dominant contribution to a specific gravitational wave mode. And it has a distinct frequency and time dependence from the main part of the signal. It has a different sort of polarization and sky pattern. So there is something that you can identify in the signal, namely this contribution to the strain from this flux term that you can use as sort of your proxy for detecting the memory with LIGO. So yeah, Andy, you had a question. I think in practice, it's actually seismic noise. If you imagine LIGO's a pendulum with whatever, a meter long, and then, kind of the characteristic oscillation frequency is root G over L. So it's, whatever that is, 0.5 hertz or something, right? So kind of the time scale of this restoring force is less than a hertz, but the ground's just moving so much that you really can't calibrate it below 10 hertz. So I think the issue is more that LIGO's stuck on Earth. And there's just random accelerations, due to seismic motion. I think that's probably more important. People try to improve this by essentially going underground like Einstein telescope, because then you cancel out more seismic noise. You get, in some sense, some shielding from the Earth, or some damping from the Earth is a better way to say it. But yeah.
But also very similar. LISA would have a much longer infrared cutoff, or?
It's much lower frequency. So LISA measures down to a few times 10 to the minus 5 hertz. The thing about LISA though is it's not, in terms of the characteristic strain it measures, it's not as sensitive. So it in principle would be hard for it to actually measure the memory from a stellar mass binary black hole.
Yeah.
So you'd have to measure it from a supermassive.
Yeah.
But then the time scale of a supermassive black hole merger, just scales with the mass. So instead of being, the times, I must have a signal somewhere. Let me just jump ahead here, right? So the time scale over which LIGO, measures the accumulation of the memory, right, is like 50 milliseconds or 50, 100 milliseconds, right? So with LISA, if you scale this up by a factor of 10 to the 4, right, then you're at whatever I said, right? That's, I don't know, 15 minutes or something, approaching an hour, right? So like the memory grows much more slowly. So, given that the low frequency cutoff is more like 10 to the minus 5, I think essentially you'd see the memory hanging around longer in LISA, right? But eventually LISA does have a low frequency cutoff because there are two sources of noise, right? LISA is a test mass with a satellite that the test mass is freely falling and the satellite kind of adjusts its motion around it. But this produces a kind of acceleration noise, which is one of the low frequency noise sources. And plus there just are cosmic rays that hit the test mass. The test mass is a block of gold and platinum, so valuable test mass. But it charges it up and then you have to discharge it, and this random, charging and discharging has some electromagnetic forces and then causes just some stochastic motion of this test mass. So, it's not perfect, but with LISA, the memory signal kind of hangs around longer before the random motion of the test mass, then sort of erases the calibration that you do to get the strain, right? So it's a better measurement, but the thing about LISA, it launches in 2035. It takes a year or two to get there. The first data comes, a year or two later, so it's 2040. And then you actually have to wait for a supermassive binary black hole merger to happen during the LISA timescale. So, it's a bit of a waiting game. So the goal here is, what can we do to speed this up? Is there something we can do with LIGO in, say, maybe the next 5 to 10 years rather than 15 to 20 or 30 or something for pulsar timing? Okay, so let me just give sort of an intuitive picture of what the memory effect, and show why there really is a distinct memory signal that you can measure in LIGO. All right, so this is what I'm calling the Newtonian expectations. And for those of you who are here on Monday, while I was getting very caught up in factors of G and so on. So right, if you compute the memory for this binary, right, what you can show basically is the strain that you accumulate is some overall factor times the change in the Newtonian potential of this binary. So namely, you get an accumulation of the memory effect due to the fact that in a Newtonian language, as your binary moves closer together, your potential energy has changed, and there's a kind of energy balance, right? The change in the potential has to get radiated away, and the signal that you get is just proportional to the change in the potential times some complicated angle-dependent function around the source, because there's actually some asymmetry. You radiate in a quadrupolar pattern. And you can continue this calculation to very high orders if you like. I think it's now been done up to 4 PN or 3.5 PN, but obviously I won't show these expressions. So what's interesting is Keith Mittman and collaborators in 2020 essentially did a numerical relativity simulation using a different technique called Cauchy characteristic extraction, where they could robustly get the 2-0 spherical harmonic component of the signal, which had been very hard for numerical relativity to model before. And what's going on here is, in this interval between the dashed lines, they're essentially checking against this post-Newtonian formula, and they find that their signal agrees very well. And then what they're computing here in this dashed orange or reddish line is essentially the contribution just from the nu squared term, just from the effective stress energy of gravitational waves, and comparing against the full signal, which also has some contributions from the charge part, the delta M, the change in the mass aspect. And as you can see, right, the nonlinear part of the signal is the dominant contribution, right? So you can essentially just use the term that the flux term as your proxy, and you don't lose very much if you ignore sort of the charge part, the part that comes from the mass aspect. Okay, so this is sort of a key thing, that there is a very distinctive signal that you can measure, and you're not really missing information by making this approximation. Okay, so then let me go back to this signal, right? So sort of the dirty secret in LIGO is, when they analyze gravitational waves, they use this signal here, which is not the correct signal in general relativity, right? It doesn't have the memory offset. If you compute this flux term, as I've shown, right, it grows as a function of time. So the true signal should look something like this, right? This is what GR predicts. So you can, if you want to detect the memory, there's two kinds of approaches that people think about. So there's the Bayesian kind of approach, which is, right, I have two hypotheses here. I have the correct signal in GR and the incorrect signal that people use for convenience. which is the better fit to the data. There's a framework of Bayesian evidence or hypothesis testing that is designed precisely to do this, which essentially computes something called the evidence ratio. Alternately, you can think of doing a kind of subtraction procedure and saying, imagine I subtract off the best fit waveform, is there some residual signal? So you can compute, say, sort of a signal to noise of this. This in practice is harder to do in real data, but it's the more convenient approach if you want to estimate, say, how long it will take to actually detect the memory from binary black hole mergers. All right, so if you take this signal to noise ratio approach, essentially what you do is it's easiest to do the analysis in the frequency domain. So you essentially compute this signal to noise ratio squared, which is just an integral of the square of the signal power divided by the noise. So at the power spectral density of the noise, the square of the LIGO noise curve that I showed earlier. And as you can see, like I just plotted the O3A detections, since this is a bit old, essentially all the events are significantly smaller than, say, somewhere around a signal to noise 3, where signal to noise to first approximation is just the significance of the detection in standard deviations in sigma, right? So here it's saying most of the events have a kind of significance of 0.1 sigma, which is not very good. All right, so to get something that's greater than 3, you need an event basically that's whatever that is, 20 or 30 times closer. So it's 20 or 30 cubed rarer. So you're waiting around for centuries essentially. So this is not a good strategy. Okay, so what is a better strategy was something that's identified by Paul Lasky and collaborators, where it's a rather busy and complicated plot, but I'll try to make sense of it for you. So what they did is they simulated a large number of synthetic populations, just like the first event. I mean, absolutely identical in mass and spin and so on, just at different points in the sky, different orientations and so on. And then they repeated this 100 or so times. And what they computed essentially is a signal to noise, not of each individual event, but a signal to noise of the total population of events. So why this is interesting is, essentially the intuitive way of thinking about it is, right, the signals add coherently. So if you add n signals squared, then the signal power grows like n. If you add n noise realizations, then from Brownian motion, it goes like root n. So this total signal to noise grows like the square root of the number of events that you have. So if you had essentially 100 events just like the first one, which sadly turned out to be sort of the loudest and one of the closer events, so it's not representative, then it's saying with 100 events, you can essentially find statistical evidence for the memory effect in the entire population of mergers, not from any single event, just from the sub-threshold mergers. So, this is encouraging. I'd say the discouraging part is the following. So essentially, after LIGO measured, the first 100 or so events, it made essentially a model for what's the rate of mergers in their favorite units as a function of primary mass. So you can think of this as a volume of space, gigaparsecs, per year, and then it's a differential rate, with respect to the primary mass. So, essentially the distribution that's actually been empirically found, the median value is this funny shaped blue curve here, and then there's some spread, which is the uncertainty based on just, the statistical uncertainties of the measurements, basically. All right, so if you're an astrophysicist, this is probably one of the most remarkable achievements of LIGO, because essentially people who tried to predict the rate theoretically found, almost anything in this range, and now it's pinned down to a factor of 2. From the perspective of measuring the memory effect, right, we now have a better idea of what the distribution of events looks like, so we can get more concrete predictions of how long it will take to detect the memory effect. Okay, so with a postdoc, Alex Grant, who's now currently in postdoc in Southampton, we essentially did this study where we updated what Lasky et al. Did. And already this is this is from 2023 already. This turns out to be a bit more optimistic than what's happened in practice. But 04 is the run that's going on now and will end in October. And we assumed that Virgo and Kagra would reach their design sensitivities, which sadly they did not. But if you were to say have 04 proceed, then again, we made many different realizations of this synthetic set of mergers of binary black holes, and we computed kind of a 1 sigma uncertainty region and a median value. After a year and a half, this signal to noise, which we're calling rho here, would be less than 1. So don't expect to detect the memory effect from the events that are coming in the next couple or next few years as LIGO finally publishes all these results. So what this interesting jump is here is, right, there's a plan essentially to improve LIGO to a configuration and do a 5th observing run, which will start sometime in around 2027 if all goes according to plan. And there's also a plan to essentially build a detector in India. And this is what's called I here. So if once these detectors reach their design sensitivity, then essentially within a few years of observing, they will be able to get, say, something like a 3 sigma and potentially even a 5 sigma significant detection of the memory. So this is the encouraging news. Just to give you sort of an idea of how many detections, it's going to require several thousands of detections over these 4 or 5 year periods. But it's something that seems within the range of the current facilities if they reach their design sensitivity and continue to operate as expected. Okay, so this I think is the encouraging thing. You don't need to wait for the next generation of detectors or essentially with pulsar timing, you need the next generation of radio telescopes to detect them. This can be done basically with projects. 05 is nominally approved as of 2024, let's say. 2025 has been a mystery, of course. Yeah, Andy. Advanced LIGO is 04. It's what's running now. Yeah. So LIGO, it's sort of at its design sensitivity. So 01, 2, and 3, we're building up to it. 04 is nominally at the design sensitivity. I don't know exactly if they've reached the goals, but it's very close. So Virgo and Kagra have not. They were sort of projected to be a little further along in terms of their sensitivity. But Kagra is supposed to join at the very end of this 04C. Okay. All right. So this is where things stand. Let me see how I'm doing on time, of course. Yeah.
10 minutes left.
Yeah.
So let me take also stimulating for questions. Do you think you could try to say something about the last part of the talk?
Yeah, I can do that. So I was just going to make a comment here that, this was a forecast. This result here, if you know what a Bayes factor is, it's essentially the ratio of the evidence for 2 hypotheses. And essentially, you'd want a log Bayes factor of on the order 4. Each of these events is an actual detection where people have done this with real data. As you can see, this is one realization. It looks not very optimistic, but people are going to keep pushing this. So it's not like people in LIGO are not actually doing this. This is now being done. There's a pipeline. So I will skip over the spin memory then, but the point is, let me just say one word about it. The point is that with the spin memory, again, there's essentially something that you can measure in the signal. Sorry for the change in notation. This is Newman-Penrose, but essentially, imaginary sigma is magnetic part of shear. F1 hat is like a scalar version of the magnetic part of the angular momentum flux. Psi 1 hat is, again, like an analog of the angular momentum charge. So again, the sort of key point is that this blue curve, the nonlinear or the flux term is essentially the dominant contribution to this 3-0 spherical harmonic mode. So again, with the spin memory, there is a distinctive signal that you can detect with principle with LIGO and Virgo. But yeah, in practice, to actually measure it, you'll have to go to the next generation of detectors. So that was, the other thing that we did with the spin memory. We sort of repeated this with the spin memory with the next generation of detectors. You need 100,000 events in many years, but yeah, it's futuristic, but it's within the realm of possibility. Okay, so let me then say a few words about these higher memory effects. Okay, so I mean, it might look like we've exhausted all the memory effects, right? Because the mass aspect has essentially the electric part of the shear in it. The angular momentum aspect equation has the magnetic part of the shear. What else can you get? So let's think about integrating the electric part of the angular momentum aspect equation, right? If you do that, you kill off the magnetic term. So you'd say, well, the memory. Well, what you find, right, is essentially there's a term here related to d squared m in the evolution equation. So if you integrate this equation, you have an integral of the mass aspect. If you integrate the mass aspect, you have two integrals of the news. So in other words, there's essentially in the angular momentum aspect, if you manipulate the lower order Bondi equations, there is a part that's related to the second or the integral of the electric part of the shear that's constrained by the angular momentum aspect. And this is what I call the center of mass memory effect. And yeah, what do I want to say about this in the interest of time? Essentially, I think the most important point is this one. If you look at the flux term, there is a part that doesn't diverge with u, right? Because if you integrate the memory with respect to u, it's going to grow with u, right? So it's going to diverge linearly in u. But there is a part related to the flux that does not diverge. And since LIGO measures strain, you can think about differentiating this equation once more. And there's a contribution to the shear, which again is something in principle LIGO could measure. But it turns out to be, say, a small contribution to one of the higher multipole moments of the shear. So it looked, at least back in 2018, I thought it was not particularly optimistic that it would ever be measured. All right, so this is kind of where things stand. If you think, we call these things moments of the news. This is Alex Grant's terminology. So the 0th moment integrating the news just gives you the gravitational wave memory. The first moment gives you kind of this spin and center of mass, or mass dipole is the other term that people use. The charge is the one conjugate to Lorentz boosts. But you can essentially iterate this procedure using the next evolution equation, the one for E. And this is what I'm calling sort of the first of the higher memory, or it's what Alex Grant called ballistic memory, which is related to the evolution of this quadrupole aspect. Okay, so what is it? Well, let me go to this equation here, right? Suppose you want to integrate this equation. So then the change in E is related to the integral of the angular momentum aspect. The integral of the angular momentum aspect has now two integrals of the mass aspect. So then it has three integrals of the shear, or sorry, of the news, or two integrals of the shear. So if you play the same game, essentially, of manipulating the Einstein equations, then you can essentially get this next higher order memory effect from the second moment of the news that's related to now two integrals of the shear, or three integrals of the news, basically. And what was interesting is I didn't spell this out on the slides, but essentially, if you then try to look for a term that's related to the contribution to the shear by differentiating this equation twice, you have this kind of flux term that depends only on the shear. And with my student Siddhant, we did some calculations and found that it was actually a post-Newtonian, or 2.5 post-Newtonian order effect. So it's kind of the same order as the spin memory. What's sort of a little bit, what's been puzzling us, and why I don't really have results for this yet, is that it's essentially just, if you look at which multipole moments it appears in, it's just the quadrupole moments, so the same multipole moments as the dominant part of the shear. So the question is, can we actually find something that is distinguishable when, at least at post-Newtonian order, it essentially is just a tiny correction to the dominant part of the signal. So we thought we had a way of doing this. It turns out, yeah, we neglected something, so I don't actually have any results for this. But we're sort of at the stage where we're thinking about, whether there's a way we can actually get some evidence of, how does sort of the evolution of this quadrupole aspect constrain parts of the gravitational waves? At the post-Newtonian order, we can compare with post-Newtonian formulas, things agree, it's definitely there, but the question is how important are sort of these charge contributions here compared with the flux contributions that we're computing? That's what we haven't sorted out, and how well we can sort of come up, as we did with the displacement or the spin memory, of a definite part of the signal that we can distinguish from other parts of the signal that we could say is related to these higher order memories and higher order charges. So yeah, I left almost no time for questions, so I'll just sort of give the summary here, leave it up there, and hopefully I have a little more time to answer questions. So yeah, thank you.
Thanks for the great talk. I wanted to know if there's any meaningful way in which PTA measurements could be, in some sense, synced with the LIGO, Virgo, Kagra type of measurements?
Yeah, I think PTA would be challenging just because the range of frequencies are so different, right? Pulsar, I'd have to go back all the way to the beginning, but pulsar timing measurements, right? The frequency band where they measure is something like 1/15 years at the low end, and then, right, made it, okay. Right, so essentially, right, the range is 1/15 years or so at the lower end, and then in practice, right, time on radio telescopes is expensive. You can't just point a radio telescope at pulsars all the time. So in practice, they measure them like once a month. Their modeling of it is so good that they actually, know when the next pulse is coming, so they can do it, but they can't really measure things on frequency ranges that are, say below or higher frequencies than 10 to the -6 hertz. So kind of linking things at 10 hertz to 10 to the -6 hertz is difficult. What can be done, in principle, there are some sources that you can measure, say, both in ground-based detectors and in space-based detectors, like they start in spiraling, and LISA catches, the very early in spiral, and then LIGO, or probably Cosmic Explorer, would catch the merger, basically. So this is a little more promising, and people call this multi-band gravitational wave astronomy because you're using multiple detectors.
Any more questions?
Can you explain a little bit more of what you mean by ballistic memory? Because you mentioned, I think on the slide that you said it's an oscillatory effect. Does that mean that it's not like a DC offset, like the leading gravitational memory effect?
Yeah, let me clarify that. So what I mean is that there is a DC. Yeah, maybe the simplest way to think about it is, right, essentially the memory effect at 0th order is you're trying to measure a step function. The spin memory effect at 0th order, you're trying to measure some kind of delta function here. And then, what these ballistic memories are, if you want to measure a non-oscillatory effect, you want to measure something that's like a derivative of a delta function. So, as a distribution, it's some, weird looking thing like this or something, right? Okay, so in principle, there is this kind of offset. What I was saying about the oscillatory part is that what is the largest contribution? Like there's a hierarchy of the spherical harmonic modes for LIGO. So the L = 2, M = 2 is the dominant one. So then you say, all right, I want to construct a nonlinear term from, say, the L = 2, M = 2 mode, and say also perhaps like the L = 2, M = 0 mode. Which modes does that appear? And if you do, your angular momentum coupling or addition formulas, it turns out the largest contribution appears in the 2-2 mode. There is going to be a n = 0 mode, but it turns out it's highly suppressed. So yeah, we just thought it was kind of extremely difficult to measure. So we were looking at the largest contribution, which turns out to be in this oscillatory signal. But there are, again, DC effects, and kind of we're looking for, in some sense, the mass aspect at 0th order produces a signal like this, the angular momentum aspect produces this delta function, and then these ballistic memories are sort of looking for a contribution to the waveform that's like a derivative of the delta function, essentially.
So let's thank David again.